Welcome everyone to ETI4205, Module 15, Logistics and Supportability Analysis. I'm excited to dive into this topic, which is absolutely critical for the long-term success of any complex system, whether we are talking about military defense systems, commercial aircraft, or even large manufacturing plants. Today, we are focusing squarely on the supportability analysis, or SA. If we design a cutting-edge piece of equipment, but forget how to fix it, maintain it, and supply with parts, the equipment is useless. And SA is the process that prevents that costly mistake. So what is supportability analysis? Simply put, the SA process is an iterative and continuous analysis. Think of it as a constant loop of checking and refining. It's not a one-time checklist. We keep on analyzing, improving, and integrating various techniques and methods throughout a system life cycle. Now, why go through this continuous process? The goal of the SA are ambitious, and they start right at the beginning during the conceptual design phase. The following two slides outline 5 main objectives for supportability analysis, and they provide a clear roadmap for our work. First, SA help us establish those critical initial supportability requirements early on during the conceptual design. If we know how supportable the system needs to be on day one, we can design appropriately. Second, SA help us establish supportability design tool criteria. This is key. We define system operational requirements, the overall maintenance concept, and we identify and prioritize technical performance measures. We also use functional analysis to allocate requirements, meaning we decide which subsystem need to meet which specific support targets. The third objective of applying SA is to conduct important design trade-off studies. A classic example here is the repair level decision. Should we throw away a broken component, fix it locally on spot, or send it back to a central facility? SA help us determine the most cost-effective solution. Fourth, SA aids in identifying necessary logistics resource requirements. Once the design is fixed, we need to know exactly what people, spare parts, and tools are needed to keep it running. And finally, objective number 5, SA help us measure and evaluate an operating system. We assess its actual degree of supportability when it's out there in the user environment. This brings us back to the idea of continuous improvement. Whether we are tackling an SA challenge or almost any other kind of complex engineering problems, we follow a structured approach. The analysis process has 7 standard steps. First one is problem definition, clear state what we are trying to solve. Second is definition of system requirements. What must the solution achieve? And third is selection of evaluation criteria. How will we measure success? And fourth is selection of a model or tools, choosing the right analytical method. And the fifth one is the data generation and application, which means collecting and applying the necessary information. And the sixth is evaluation and selection of a preferred design approach to make the final choice. And last but not least, we need to document the results and write down everything we did and why. Now let's move on to the specific tools and methods we use to execute supportability analysis. The slide highlights several critique techniques, starting with the life cycle cost analysis, or LCAA. LCCA is a focus on understanding costs throughout the system's entire life, from design to disposal. For LCCA, we define the problem, analyze the approach, and generate results. This helps us to meet those design two criteria we discussed earlier. Next up is the failure mode effects and the criticality analysis, short for FMEA, or its close relative, failure mode and effects analysis, FMEA. Again, we define the problem, figure out the analysis approach, often using the functional flow diagram, and review the results. These tools are foundational for predicting potential failures and understanding their consequences. One of the most powerful and visual methods used in failure analysis is the cause and effect diagram. You might also hear this called the fishbone diagram or the Ishikawa diagram, named after Dr. Karo Ishikawa, who developed this tool in 1943. This diagram is essentially a picture consists of lines and symbols designed to show a meaningful relationship between a defined effect and all its potential causes. The effect or the characteristic that needs improvement is placed on the right, and all the causes branches of the left side. For logistics, we often characterize courses into main groups, sometimes called the 6 M's, such as people, materials, equipment, measurement, work methods, and environment. Primary causes lead to the secondary causes, and both causes will create a detailed map. The steps for building this diagram are systematic. So first, we need to identify the effect of or a quality problem. Then determine the major causes, like manpower or materials. Then we determine all other minor causes, which also called the secondary causes. This usually requires some brainstorming session. Once the diagram is complete, we evaluate it to determine the most likely causes. And finally, we develop solutions. Okay, let's quickly look at one example from this slide. The problem or the effect in this case is the reports not printed within time frame, which we put this as the effect to the right end of the fishbone diagram. And starting from this effect, we need to figure out the causes which lead to this problem. The second step is to determine the main causes. So during the main storm session, we might be able to identify major causes, such as materials, machinery, manpower, and methodology. And by brainstorming, we can also further break this down. Under these major causes, we can further break down them into minor causes. For example, under manpower, we might find issues like no training or poor proofreading. Under machinery, we might find the frequent breakdowns, and all those require some brainstorm session. After evaluating, we need to pinpoint the actual causes. The fourth step is to determine the actual causes. In this specific example, we might conclude that the actual causes are poor proofreading, frequent breakdowns, late proofreading and setting, and not enough funds. The final step is to arrange these actual causes by priority. Among those actual causes, we need to set a different priority to them respectively, and this prioritization allows us to attack the biggest logistical bottleneck first. Beyond FMECA and the Ishikawa diagram, we also have a few other specialized tools vital for supportability. First, fault tree analysis, or FTA. FTA is another failure analysis technique where we start with top-level undesired desired event or top event. And this analysis approach involved 3 steps. First, to identifying the top-level event, developing the fault tree, which logically link lower-level failure to the top event, and then analyze the complete tree. Second tool is we call it maintenance task analysis, or MTA. This helps us evaluate the labor, cost, or time required to perform specific maintenance actions. The approach involves reviewing historic information, performing the task analysis to evaluate cost, and then evaluating the information presented. Our third tool is reliability-centered maintenance, short RCM. RCM is focusing on optimizing maintenance programs by asking what needs to be maintained. Its approach involves identifying the critical system functions or components, applying the RCM decision logic to develop the preventive maintenance program, and then implementing and evaluating that preventive maintenance program's effectiveness. RCM helps ensure that we spend maintenance dollars on the items that truly matter for system functionality. Finally, let's talk about how all this information, the requirements, the costs, the failing data is managed and utilized, particularly in large environments like the Department of Defense. This is where Logistic Management Information, or LMI, comes in. LMI essentially replaced the older Logistics Supportability Analysis Standard, or LSA. It is fundamentally about data management. LMI defines the data elements required for crucial activity like the provision, getting the right parts, cataloging, and managing support equipment. This data is to assess the design the support structure and develop integrated logistics support or the products. And the key concept within LMI is that it should be flexible and require minimum program oversight. Importantly, LMI describes what is required, not how to produce it. In this slide, we highlighted the data item description, or DID, documents. These DIDs are essential because they allow the government to obtain specific data products from industry partners, which then feed into in-house provisioning and support equipment systems. This data product populate automated data processing, short ADP, also known as ADP systems. DID also covers data summaries. These summaries allow for in-house logistics planning during the acquisition phase to ensure that a cost-effective, efficient support structure is ready when the system is fielded. Ultimately, this information is vital for planning, assessing program status, and making major decisions. For acquisition logistics, the guidance emphasizes tailoring the LMI and DID worksheets and incorporating supportability requirements and analysis directly into the system engineering process. And supportability must be integrated, not bolted on afterwards. Okay, let's wrap up our lecture with some conclusions. Supportability analysis is a continuous, systematic method to ensure that a system is not only effective, but also maintainable and affordable throughout its entire service life. We leverage powerful tools from LCCA to Ishikawa diagram and RCM, all supported by robust logistic management information system. The goal, whether we are analyzing a logistic problem or designing a system, is to use these structured methods to identify weaknesses and prioritize solutions. It's like being a detective for efficiency, always trying to find the root causes, whether it's not enough funds or frequent breakdown in our example. If you have any questions, feel free to contact me, and thanks for spending your time with me.